Okay, so last week in we were in chapter 2, so we have done some of the example regarding the Verilog modeling style, where we have 3 modeling style, which is the data flow modeling, behavioral modeling, and structural modeling. So today we will continue on that. Continue with the other example. Using the same, the same circuit, right? But last week we have looked at how we model the multiplexer, 2-to-1 multiplexer, using the data flow modeling. So today we will use the same circuit, which is the 2-to-1 multiplexer, to now we want to model that circuit using behavioral modeling. Yeah. So today still we will use the software, yeah, in order to practice, to understand this. So you need software. So make sure that you have Quartus Prime with you, or Quartus 2. Okay, so before we model using behavioral modeling, let's do some revision. Look at what we have done last week. Right, so we have hopefully you can see my screen clearly. So let's open our the last week project. Okay, you can just open. You can go to open your file, or you go to recent project and choose the one that the recent one, or the one that you opened last week. So in this case, this is the our marks. We model or describe the 2-to-1 multiplexer using data flow modeling. Why is this data flow modeling? Easy. Look at this. We have this assign statement. Yeah, assign, and we have the Boolean equation, and this is definitely the data flow modeling. Right? Very easy. And when we do the simulation, right, you can run the tools RTL simulation. And the simulation is based on the attachment. Yeah, so this is the attachment file that was designed or created last week. So this is to demonstrate the functionality of the 2-to-1 multiplexer. So here we can see that all the input combinations are provided. Yeah, because we have, remember, we have A and B, and also the S for the select. Yeah. Right. So we have the multiplexer. We have input A, B, and we have the control S, and we have the output name F here, right? So yeah, for any logic circuit, if we have three inputs like this, so the possible input combination will be uh, 8, up to 8 combinations. So here we have 8 combination from 0, 0, 0 to 1, 1, 1, right? So we test all the combination that that is possible, right? And when we run the simulation, okay, so this is the simulation, and this is the waveform. And also when we write like this, when we have this, yeah, monitor and time, we want to see time unit, right? So remember, when we do simulation, means that we want to see the changing of input and output, yeah, or the relation of input and output uh, relative to time, right? So okay, we will have the this is the actually voltage and relative to time t. So when we write this, means that we will look at the time when time 0 and a is equal to 0, 0 b equal to 0, s equal to 0, and what is f, right? So when we simulate, clearly we can get this. This part is available because this, when we remove this part of code, we will don't have this. We will have only the the waveform, right? So when we look at this, yeah, and we compare to this, right? So we can see that 0, 0, 0, we have f equal to 0, 0, 0, 1, we have f equal to 1, and so on. The output, right, is actually very easy to verify because according to the multiplexer behavior, yeah, if s equal to 0, so the output f should be equal to b, and if s equal to 1, the output f should be equal to a. So this is exactly what we want, right? Easy for that. Now we can close this. Okay, and we want to model, yeah, now we want to model our circuit using behavioral modeling. So to do that, we can have a new project. Yeah, close this one. You can close this one. But for that, I want to copy this because I will actually use the same attachment, right? Because the attachment should be the same. The only difference is that how you uh, have this, yeah. Or maybe we can, yeah, just change here, yeah. So we can use the same attachment here. Okay, so let me change this to the behavioral modeling. So to have behavioral modeling, the difference is that how we describe the body of the code is different. So to do that, we need to have an always block, and the sensitivity list. So what is sensitivity list? So this is the list of the signal, yeah, that the output sensitive to, right? So in our case, our output is sensitive to these three signals. So we put here A, you can write A or B or S, or you can simply put comma, right? So it is the same, yeah, always. And how many statements you want to have after the always block? If you have more than one statement, you need to have a begin and you need to have an end, right? So in our case, because this is very simple circuit, we only have one statement, right? So for the behavioral modeling, we don't need Boolean equation, right? We just describe the behavior of the circuit. So we can use if, yeah? So if S equal to 1, what is the output? If S equal to 0, what is the output? So in this case, we can start with if S equal to 1, or you can simply write like this, same thing. F should be equal to, if S equal to 1, should be equal to A, right? Else means that if S equal to 0, F should be equal to B, right? So this is done. Okay, so this is our behavioral code using if-else statement, and this is consider one statement, yeah, because we have only one if, right? If you have more than that, so you need begin and end. All right, in this case, again, when you code in behavioral modeling, all right, means that you will assign values, yeah, to the variable, and f now is a variable, right? So in behavioral modeling, this f must be declared as right as well, right? And in our case, of course, f is an output, and also f is a rect, because f is a variable inside the always block. So you need to have this. If not, when you compile the design, you will get the error message. Okay, so I think this is done. So we can now do the analysis and synthesis again. We need to save first. Okay, save. Okay, should be done. We have 0 errors and 1 warning. And again, the warning is okay, because this is about this setting. So should be no problem then. And still, the attachment is still the same, because the input and output is still the same. So we have this as our attachment, and the setting is, yeah, no need to do any other setting, because we have done this in our previous design, right? So and everything is okay now, so we can go ahead and run the simulation. So we can choose this RTL simulation, or you can go to tools, run simulation tools, RTL simulation, and see the result later on. Okay, our result is here, done. So in terms of waveform, this is the waveform, and let's look at the output. So here is the output. We can see that if S equal to 0 and A should be equal, F it should be equal to A, should be equal to B. Yeah, and if S equal to 1, F should be equal to A. So exactly the same with the previous one, and you can see that, yeah, we get the now we get the same circuit, but using different modeling, right? So again, we can choose which modeling style that we want to code in order to describe the digital circuit. So based on which one is more suitable in certain uh, based on design specification that we have. In this case, we can model using data flow modeling, but of course, using data flow modeling, you need to have or derive the Boolean equation. So you need to have the uh, truth table, and then you have your K-map, and then you can derive the Boolean equation from that. Now, what about this structural modeling? So to model using structural modeling, you need to have this schematic, all right? Because structural modeling means you describe your circuit based on the circuit structure or the connection of the circuit, all right? Which this node, for example, is connected to this node, and this node is the input to this gate, and this gate, this node is the output to this gate, and so on. Right? So again, we need a schematic, right? So if you look at the Boolean equation for the 2-to-1 multiplexer, so it should be F equal to A as A or S bar B, right? So we have the AND gate where we have A, we have S, and we have another one which is NOT gate, and this is B, and we have O, and this should be F. Okay, so this will be our schematic of a 2-to-1 multiplexer. And of course, because we have the wire here, so we need a label, the label name, all right? So let's have this label as I, and this one is I, and this one is J, all right? And this one you want to label, or you want to use only the not symbol also can. So it's better to use a not symbol, easier to write in the code. Okay, now we want to describe this. Again, we use the same design here. Okay, in this case, we don't have this. And of course, we have a new one, declaration, a wire, right? We have two wires, I and J. And now we describe this. So we can start with any gate, any gate. For example, if you want to start with this one, should be no problem. So this is all. And of course, you need to have the output first, followed by the input. All right, so you have F, I, and J. What about this one? Okay, so it will be an AND gate. So you have the output J, and you have NOT S, and you have B, and you can have this one is an AND gate, and the output is I, and you have A, S, and A, or A and S. All right. So this is based on the structure of the circuit. You see, that is why we call it structural modeling. And again, we save and we synthesis and analysis and synthesis. Okay, so now we have no error and one warning, and of course the same warning should be no problem. Now we still use the same dashband, and we can straight away proceed to simulation. So you go to simulation and run the simulation, and before that we need to close this. Right, but if you want to use the same window, it's also can, yeah, where you can all right, instead of you start your simulation from quarters, actually you can do the simulation here, right, where you can do this, yeah, where you end the simulation, the previous simulation here. You go to simulate, click end simulation. Okay, quit. Right. Now you want to start a simulation, right? So to start the simulation, you need to compile the detachment that is created previously, yeah, which is this one, yeah. So you just click this and click compile, right? So you look at this. If you don't have any error, means that your attachment file is okay. You click done, and you go to simulate. You click start simulation, and you will have this. You go to RTL work, this one, yeah, click this, click OK, yeah, okay, and if we run the simulation again, not run yet, you need to click run all, and now it's run the simulation. So you can see it will produce the same output. For here, you need to select this and move to here, and you can actually run again. All right, look at this. We'll have the same output as the previous one, where if S equal to 0, F should be equal to B, and if S equal to 1, F should be equal to A. So this is exactly the same, but using the different modeling technique, right? So I hope that you can differentiate or know already that the difference between these three modeling style is yeah, this based on the example that we just discussed. So again, you can model your digital circuit using these three modeling style, but it's depend on the specification, depend on circuit that we want to model, and also depend on your experience. Yeah, when you start to code in Verilog, and after you do some design and you get experience, you gain the experience from time to time, and you will know exactly what is the modeling style that you need to use. Yeah, and when you want to describe the digital circuit, right? So if you ask me what modeling style that you need to use in order to model your circuit, my answer is all the three modeling style can be used, but it depends on the circuit that you want to describe, and also depend on your experience in Verilog coding, right? So this will be a good start, yeah, to familiar with this, and and I think the example given is a good example, right? So that you can differentiate between these three modeling style. Okay, so I think that is should be clear enough for that. So any question before we proceed to the next? Yeah, this is just another example, so you can try this on your own. Okay, if no question, means that good. Okay, so this is another example. So data flow modeling, of course, you need to have the equation. So this is the equation, and you use the assign keyword, right? So you assign, and you have the equation. So the equation is based on the circuit. Okay, if you don't have the circuit, of course, you need to derive based on the truth table, right? And this is another example. Yeah, assign keyword. You see, if you have assign keyword, then you can have your circuit. Yeah, another example. Behavioral modeling, right? So we will use the statement or keyword that resemble the computer programming. Right? The syntax is more similar to computer programming style, where you use if, else statement, you use case statement, you use for loop, all right, you use while statement. Okay, so that are behavioral modeling, right? So for example, this if x equal to 0 and y equal to 0, z should be equal to 0, else, yeah, means that other than that, z equal to 1, right? So this is an OR gate, this is an AND gate. This model using behavioral modeling. Structural modeling, of course, you need uh, a schematic, right? And you describe using this keyword. Yeah, if you want to create an AND gate, so this is the keyword AND gate, OR gate, and so on. Okay, so this is an example using the same circuit as previous one, and now you model using structural modeling. All right. Next, we will go to the synthesis of design. Synthesis means the process of converting the design specified in the hardware description language. Means that your code in Verilog into a form of suitable for manufacture, or into a form that can be loaded to a programmable device such as FPGA. So it depends on what is the target technology that you want to use. So if you want to create the custom chip or custom design, the ASIC, yeah, then it will it will be converted to the schematic that will be converted to the custom design chip, right? So if you use FPGA, so it will be translated into the logic that, yeah, we have looked at this in chapter 1 already. FPGA is programmed based on the logic in the LUT, right? Or in other words, the synthesis is the process of converting from code to the circuit. That's it. All right. Yeah, this is a synthesis is a process of converting a high-level description. So Verilog or VHDL is the high-level description. Yeah, is the description of a circuit using a language to the gate level representation or the circuit. So logic synthesis uses a standard cell library. We have simple cells such as AND gate, OR gate, NOR gate, or macro cells such as adder, muxes, and muxes is a multiplexer, memory, and flip-flop, and so on. All right. So when we do the synthesis in our program, in our quarters here, right, we click the analysis and synthesis. So the program, the software, will convert the code to the gate level description. Right. That is the meaning of synthesis. So it is done by, of course, the synthesis tool. Yeah, in our case is the quarters, but as a programmer, as a designer ourselves, we need to understand, or we need to know, right, the process of synthesis. All right. So when we write the code, to be a good programmer, hardware designer, all right. So we need to know, when we write the code like this, we need to know what is the circuit that the computer will produce later on. Okay, so that is a very important skill, and in this part we will learn that skill. All right, where from the, yeah, if you are given the code like this, the Verilog code like this, so you should be able to produce the circuit, the gate level representation of this, or at least in the form of the block diagram. What is this wire, for example, connected to another wire or another port. Okay, so in this case, for example, if we have this data flow modeling style like this, yeah, it is easy to synthesize to the circuit, because you have the Boolean equation. So this is very easy for us to convert to circuit. So for example, x equal to, should be not, and a XOR b. So we have a XOR b, and we have not, and we have x. Yeah. So this is exactly this part. And we have the second part, which is y. And y is a and b, or a and c or b. So we can see that we have not a, sorry, x, x and c. So we have x here, x, and we have and c, and we OR with b, and we have y. All right. So that is how it is synthesized into the gate level representation. Another example using structural modeling here. All right, the same circuit. Yeah, this is the same circuit. So now if you are given the structural code like this, you should be able to convert this code or derive the circuit also from the code. So this is still okay, it's same, but first you need to label this. So XOR, you have XOR, then this is T1, all right, T1, AB, AB, T1, and you have not gate, and the output is X, T1, yeah, this one, and you have this AND gate, and the output is T2, and the input is X and C, and the last one is the OR gate. So you have Y, T2, and B, right? As simple as that. And also for the behavioral code, yeah, now we have the data flow, we have the structure, behavioral code. The behavioral code is not that easy. Yeah, the easiest synthesis process is from data flow code or structural code. Yeah, to get the circuit from that to modeling style is quite straightforward. But for behavioral modeling, to synthesize is not straightforward because we need to understand what is the behavior, the description, the behavior of the circuit based on this behavioral code, right? So it's not easy, right? When you when we look at this, see, we have two always block here, right? And look at the first one. We have if A equal to B. This is the statement that follow the if else, yeah? So if A equal to B, T1 equal to 0, else T1 equal to 1. So when we look at this, we don't know yet what is the gate that this code will synthesize to, all right? So it's not that easy, right? So from that, we need to extract the information from here. So if A equal to B, T1 equal to 0, else T1 equal to 1. So yeah, we from here we can say that we have two input A and B, right? And we have one output T1, right? So we can have if two input, one output, the truth table is easy. So we can have a truth table where we have A, we have B, and we have T1 as our output. And of course, if we have two input, so we will have four input, possible input combination. Okay, so let's look at the behavior. If A equal to B, T1 should be equal to 0. So which one is when A equal to B? So here A equal to 0, B equal to 0, and another one is here, right? When A equal to 1 and B equal to 1. Here A not equal to B, here A not equal to B, right? So these two. So if A and A equal to B, the output T1 should be equal to 0. So this should be equal to 0. And else, other than that, means that these two, T1 should be equal to 1. Right? So from this is clearly, when we look at this is clearly an XOR behavior or XOR gate. Now we can synthesize this to an XOR, where this is A, B, and this is T1. For this part. And we have another one. X is equal to not T1. Means that we have we have another one, which is a X here, and it is not T1, so it means that we have a NOT gate here, and we have X. For this, always block. What is this? Another one. So again, if X and C, and remember this is logical AND, right? In chapter 1, I have introduced to you what is logical AND. Logical AND is the operator that we use to test, right? So here we test, right? We use if. If X and C, this is OR B. If X and C or B equal to 1, means that if X, so we can have X and C, which is an AND gate, or B, so we have B, or Y equal to 1. If this correct, means that Y equal to 1, means it's Y. All right, if X and C or B, Y equal to 1. So the circuit should be like this. Else means that other than that, Y equal to 0. Or you can have the truth table. Yeah, you can have a truth table and have a K-map, have the Boolean equation, and you will get this circuit also. And this is the same as the previous one, right? But now you describe using behavioral code or behavioral modeling, right? And for the synthesis, yeah, synthesis of behavioral code is not that easy. You can see already that you need to do many things in order to create or to derive the circuit, yeah, as compared to this one, right? But of course, the advantage of behavioral modeling is that you don't need to have the Boolean equation, right, in order to code in behavioral modeling. You just write or describe the behavior of your circuit, and the computer will generate this for you. Okay. All right. So go ahead here. Yeah, this one is the actually I have explained here. This is just an another explanation. Easy for structural modeling, hard for behavioral modeling. Yeah, structural and data flow modeling actually, right? Data flow code. So this is the same. So we can skip. Yeah, we can skip. In front of you may, yep, you may have this word, yeah, in some of books, reference books. Inference means that, yeah, this substitute or infer, all right, means that to replace or to create, yeah, the circuit, yeah, based on the operator that you use. All right, if you use this, it will infer an adder, for example. All right, something like that. Okay, so again, if you use this conditional operator, all right, we have looked at this in the previous lecture. All right, so it will create or infer the multiplexer. Right, for example, if you have something like this, yeah, this is a example of inference where this one will be inferred to multiplexer, this one will be inferred to an adder, right? And the code will be synthesized to this circuit. That's it. So assign T, yeah, you use the data flow modeling, assign T equal D means that this one, D, B, double dot C. So this is what we call conditional operator, condition, yeah, D question mark, B, double dot C, semicolon. So means that B should be here, C should be here, and the output T. So if you have something like this, it will automatically, yeah, be synthesized into a multiplexer, or we call it infer to the multiplexer. If you have x equal to a plus t, so you have x, this is t, this is a, so this is the adder, all right? So this code will be synthesized to this circuit, and this part will be inferred to this. Okay. Synthesis of combinational logic from behavioral code. So we discussed already that this is not that easy, but there is the some of the things that you need to avoid in order to write the behavioral code to create a combinational circuit. What is combinational circuit? Combinational circuit or combinational logic? We will learn in detail in the next chapter, but in general, combinational circuit is the circuit that the output is or respond or change immediately after any of the input change the state. Yeah. So for example, this circuit, this is combinational. This is a combinational circuit because the output X here will change if any of these A or B or C or D change. Yeah, from yeah, if this is 1 bit, A is changed from 0 to 1 or 1 to 0, so it will immediately change the value of the output here, X, right? So that is called combinational circuit. Another type of circuit is called a sequential circuit, right? So a sequential circuit is a circuit that has a clock. All right. So for example, if you have a circuit, yeah, in a blocks like this, so you have A, you have B, and you have another signal. It's a clock, right? And you have the F. So F here is not depend on only in the depend to A and B, yeah. Not only depend to A and B, but also depend on the state of the clock, yeah, whether the clock is active or not. All right. And also the output F is also depend on the behavior of the previous previous circuit condition, all right, which we call the memory. Okay, so the circuit that the output is not only depend on the input, yeah, the changes in the input, but also depend on the memory of the circuit, and also the clock is called a sequential circuit, and we will learn sequential circuit in chapter 4. All right, so there are two types of sequential circuit. So two types of digital circuit. So to create the combinational circuit from behavioral code, there are some restriction or the things that you need to avoid. First, the code must be in an always block. Yeah, when you want to code in behavioral circuit, behavioral modeling, so you need to have your code in an always block, right? Look at this. This is behavioral code, must be in the always block. This is the behavioral code and also must be in the always block. The sensitivity list must not contain a post edge and neck edge. These two we will learn in chapter 4 when we design the sequential circuit later on to create the clock. Yeah. So if in your always block, yeah, you have the sensitivity list, right? So these are the sensitivity list A, B, X, C. So you cannot put post H or neg H in this. Yeah, that one will create a clock. So if you have clock, that is not combinational circuit anymore. So don't use this. The sensitivity list must explicitly list all reference live-in variable or consists of which does the same thing. So yeah, you need to have the sensitivity list. A variable must be always assigned in a block. A variable means that the variable that you assign in any always block, you need to declare as right. So that is the things that you need to do when you want to code or create combinational logic using behavioral code. Now let's look at this. Yeah. So this one you need to aware of when you create the combinational circuit using behavioral modeling. So look at this. You have your module, your declaration, the always block, and of course this will be a behavioral code. So you have x equal to this, y equal to this, and this is okay, will be synthesized into combinational logic based on this logic equation. All right, no problem. But when you look at the second one, you see that you have the declaration, you have the always block, and you have if statement. You have x equal to this, no problem. You have if c, y equal to this. And the problem is that this one will not be synthesized into combinational circuit because of this statement. All right. So previously, I said that if you use if statement, yes, it will create the circuit, the combinational circuit, at least, right? But you need to beware of using if. Yeah. For example, in this case, you use if c means that if c equal to 1, y equal to this, but you not state if c equal to 0, what happened, right? Or else statement. This is not wrong, but this will not be synthesized into combinational circuit, right? Because in Verilog, if you do something like this, what happened is that yeah, if c means that if c equal to 1, the output y is equal to blah blah blah, right? Equal to this. But what happened if c equal to 0? You don't have any statement on that. So when you compile the code or when you synthesize the code, you will not have any syntax error because the syntax is correct. And does the software synthesize your code? Yes, it will be synthesized, but it will not be synthesized into a combinational circuit, but it will be synthesized into a sequential circuit instead, right? Because there is a memory element here, yeah, because the Verilog compiler will have something like this. If c equal to 1, y equal to, yes, x and c or b. But if c equal to 0, because you not state what happened if c equal to 0, so the Verilog compiler will do this for you for free, right? Y equal to y. what is this mean? Means that if C equal to 0, Y remain Y, or Y is not changed. This imply memory. This is memory. Okay. So if you have a memory in circuit, so this is not combinational circuit, because you have a feedback loop and anything. So we can see in in chapter 4 later on. Okay. So rule of thumb, when you want to code your combinational circuit, when you want to describe your combinational circuit using behavioral, if you use if-else statement, make sure that you have if, yes, okay, but please state else. Yeah, else what happened? Then you will be safe. Right? If not, you will have the memory element here. All right. So your circuit will behave will not behave as your specification later on, right? If you have something like this. So make sure that you code correctly, yeah, using behavioral modeling. Okay, right. Described or discussed already, should be no problem. If statement, yeah, if you have if statement, something like this, if S equal to 1, F equal to A, else F equal to B, and of course this will be synthesized equal into a multiplexer. Yeah, we in our example just now, right? When you use case statement, so this is your first time, your first case statement. So case statement is just same case statement in C++. So it is actually a similar to if statement. Yeah, case statement is actually an if statement for if you have many input combinations, right? So if you use if else is for two input. If A equal to 1, for example, if A equal to 1, what happened? Else means that if A equal to 0, what happened? So A have only two conditions, right? 0 and 1. But if you have many conditions, for example, A is more than 1 bit, 2 bit, so you will have 4 possibilities already, right? A equal to 0, 0, 0, A equal to 0, 1, A equal to 1, 0, A equal to 1, 1, right? So if you have that, you can still use if statement, but you need to if else, else if again, else if again. So the best way is to use the case statement, right? So the case statement is something like this. For example, you have your S is 2 bit, for example, right? So if S equal to 0, 0, F equal to A. If S equal to 0, 1, F equal to B. If S equal to 1, 0, F equal to C. If S equal to 1, 1, F equal to D. And this is, of course, will be synthesized into a multiplexer as well. But this multiplexer is a 4 to 1 multiplexer, right? Where you have 4 input. Yeah, because your S now is 2-bit. And this is how we write a 2-bit signal. Yeah, S10 means that you have S0 and means that you have S0 and another one is S1, right? Or S1, S0. Okay, 2-bit. What about loop? Yeah, repeat statement or loop, right? For loop iteration 4. So this is how. So for example, you have the circuit like this. No, the Verilog code like this. Yeah, you have input, and this is your first time for the. I mean, the size of the signal is more than 1 bit. So this is how we write in Verilog. So means that your A is now not 1 bit but 4 bit. Yeah. So you will have if you write like this, okay, so actually your A is A3, A2, A1 and A0. So you will have 4 A's actually. Yeah, 4 bit. A3, A2, A1, A0. That is the meaning of this. And input B means that B is only 1 bit. Output, and this is a rack as well, because C, we want to assign something to this C, and C must be declared as rack as well. And the C is 3 bit also, 4 bit also. Yeah, 3 to 0, 4 bit. And we have another one, variable, and it is declared as an integer I. Okay, look at this, for always, and again, if this is always blocked, so here should be in behavioral code. And this is the sensitivity list. So for I equal to 0, yeah, this I, and this will not be synthesized into any wire, right? This integer. So it's just used by the Verilog compiler to create a loop. All right. For I equal to 0, I less than 4, I equal to I plus 1. So in Verilog, again, you cannot use something like I plus plus, just like in your C++, right? So if you want to increase an integer I here, so this is the way, I equal to I plus 1. Ci equal to A, I, and B. So when you look at this, so this for loop will repeated how many times depend on this condition, right? So when you so we can unroll the loop here by doing something like this. So let's have first, if I equal to 0, so what happens is, if I equal to 0, this condition is true because I is less than 4, right? So if I equal to 0, and this, because this condition is true, so this will be executed. So we will have C0 equal to A0 and B. So this is the first one. And after that, we increase I here. So I equal to 0, 0 plus 1, which is 1. So we have I equal to 1. And when I equal to 1, this condition is still correct, still true. So we have C1 equal to A1 and B. And again, we increase I. So we have I equal to 2 now. So we will have C2 equal to A2 and B. And still, I equal to 3. So we have C3 equal to A3 and B. Now I equal to 4. So when I equal to 4, this condition is untrue already. It's not true. So if not true, we will exit the loop and we will not have C4, right? So done. So when we unroll this loop, you can see that we have this C0, A0 and B, C1, A1 and B. So when we synthesize the code, we're going to get something like this. A3 and C3 is actually A3 and B. And if I equal to 2, A2, C2, A2, and B. And same as this one, A1, this one, A1 and B, we have C1. And A0 and B, we have C0. All right. So this loop will be synthesized, or this code will be synthesized into this circuit. And you can see when we use for loop, we can create a repeated structure like this, right? Which is a very good features that we can utilize whenever we want to create our circuit later on, right? So just imagine if you create your circuit using a schematic drawing, right? So if you have this structure repeated for example 100 times, how to do? You need to draw 100 times, right? But in Verilog, you just change this value, right? And also this value, and you can have your circuit already. Synthesis of sequential circuit. Yeah, when you have if without the else, it is actually will be synthesized into a latch, and a latch is a sequential circuit. We will learn in chapter 4, right? The latch and flip flops, right? The code like this. We will learn in detail in chapter 4. Yeah. So this is the behavior of a latch actually. So you can see if C equal to 1, so Q is equal to D, D latch. So else, yeah, else means that if C equal to 0, so Q will remain Q, right? The behavior of the latch. Yeah. So when you draw the timing diagram of a latch, so you can have something like this. If I have this is C, this is D, and this is Q. So let's, for example, like this. Right? So your Q will be like this. Sorry. Your Q will be go to 1 and here. Now, because here C is not active, so the Q will remain 1. And here also not active, so Q will remain 1 until C is going to 1 again. Then your Q will go down to 0. So this is the behavior of a latch, right? Means that if you write in the code, so if C equal to 1, Q should be equal to D, and this is actually if C equal to 0, Q equal to Q, right? So if you write like this, actually the behavior is like this, and this is a latch. Okay, so we will learn in detail in chapter 4. Yeah, don't worry. I think last part for this chapter is the behavioral design methodologies, how we code behavioral, and for this I will explain using example and using the quarters prime as well, so that you can understand how this is done, right? And how is this function in quarters. But before we go into detail for this, let's have a break for 10 minutes. Yeah. So any question?